Welcome back, everybody. Chapter 12, Alkanes. So we can sort of think about alkanes as a functional group, but the key, I think, to think about alkanes is that this is what sort of defines most organic compounds as organic, the idea that there's alkanes going on. So for all the different functional groups, we'll sort of do the same thing every time, which is introduce them, talk about potential isomers and descriptions, talk about how to name them, then talk about how to react them, and then talk about their physical properties. We'll do this every time. So it's a good way to get started by doing it with the building blocks of organic molecules, which are alkanes. Okay. So when we talk about the definition of what an alkane is, it is CC bonds and CH bonds, and all of them just single bonds. That's how you define what an alkane is. Now, some people get confused by the acyclic part. Alkanes that contain chains of carbon atoms but no rings are acyclic. So how do we keep this straight in our head? Let's hope that you guys have been paying attention and are trying to learn from COVID-19. You know that one of the things that makes COVID most insidious is that you can be spreading the virus even though you have no symptoms. So in other words, you are still potentially a carrier and a spreader of the virus, even if you are asymptomatic, right? So if you're asymptomatic, do you have symptoms or do you not have symptoms? And everybody knows, no symptoms, right? No fever, no chills, no loss of taste and smell, no any of those kinds of issues that are related to the COVID virus. So any alkane that contains chains of carbon atoms but no rings are considered to be acyclic alkanes. And the general formula for acyclic alkanes are C to the N, so there are N number of carbon atoms, and the number of hydrogen atoms are 2N, twice the number of carbon atoms, and then you add 2 to that. So C5H12. So if N is equal to 5, 2 times 5 plus 2 is equal to 10 plus 2, or 12. Okay, now acyclic, meaning no rings, are called saturated alkanes because they have the maximum number. If your shirt is saturated with water, that means it has all the water you can hold on it and it can't hold any more. So saturated alkanes have the maximum number of hydrogens per every carbon atom, and they can't hold any more. Okay, we'll be talking about saturated organic compounds in the future. Anybody who pays any attention at all to nutrition knows the difference between saturated and polyunsaturated fats. So that's something that we can talk about later whenever we deal with fats. This is a general organic and biological chemistry course, and that'll be one of those topics that I find pretty interesting is whenever we take the chemistry and apply it to real life and biological systems. Okay, so remember, because we have the maximum number of hydrogens per carbon, and that the carbons bond to other carbons with single bonds. Every carbon is going to have 4 bonds to it. So 1, 2, 3, 4. 1, 2, 3, 4. Every single carbon has that tetrahedral geometry. Well, we talked about acyclic alkanes. Now let's talk a little bit about cycloalkanes. Cycloalkanes have the carbon atoms that join together in one or more rings. They have the general formula of CnH2n, which means they have lost 2 hydrogens in the process of taking a acyclic alkane and turning it into a cyclic alkane. So it's easier, as you can see, to draw it like this than to draw it with all the hydrogens attached. That's why the line drawing, the line formula is usually simpler with cyclic alkanes. And whenever we talk about alkane names, they all end up with ane. So cyclohexane. We'll talk about how to do our naming shortly. So one of the things you will have to memorize is all the different fewer than 5 carbon prefixes for all the different kinds of alkanes. Methane is a 1 carbon alkane. There it is. Ethane is a 2 carbon alkane. Propane is 3. And you can see how there's lots of different ways to write them. There's the condensed formula. There's the structural formula. When we look at it in a 3-dimensional representation, we can see where the wedge has the hydrogen coming out at you. The dotted lines have the hydrogens going back into the plane of your computer screen, and the HCC bonds are in the plane of the screen. So 2 of them are sticking out or sticking into the plane, and the rest of them are in the plane. And you can see that represented by the ball and stick. So this isn't all flat. This is a sort of a pyramid with a tetrahedral line on top, and then those tetrahedrals keep going. It's important to be able to visualize the 3-dimensionality and shape of these molecules. What we're going to find out next is sometimes some of the ways that you can write formulas for compounds have 2 different kinds of representation. And you have to be able to tell the difference whether it does or it doesn't have 2 different types of representations. And the key here is to recognize that if you draw these all in a line, or if you make a right turn here, it doesn't matter. These are all equivalent. Why are they equivalent? Because the bends in a carbon chain don't matter when it comes to identifying different compounds. They have just different conformations. Think about it. If you had a 5-ring chain, 1, 2, 3, 4, 5, or you went 1, 2, 3, 4, 5, it's the same chain. You just have it arranged in a different way, and that's what we mean by conformations. But if you said 1, 2, 3, 4, 5, well, that's a different chain altogether than if there's 5 rings in a straight chain. And we'll talk about what that means very shortly. it is important that you understand and remember that when we have these simple straight chain alkanes, the bond rotation can occur around carbon-carbon single bonds. Okay, so the rotation can occur so that this can flip around. You can see that the red goes to the bottom here while the blue stays in its place. The best way and the most likely way that straight chain alkanes will arrange themselves is in this zigzag fashion. Why? Because we don't want, and it's uncomfortable whenever atoms get close to each other, because atoms consist of electrons on the outside, and the electrons don't like being close to each other. It's negative charge repulsion, and so when they get close, they get uncomfortable. They'd much rather be in that zigzag fashion. So we'll, especially in line formulas, represent them looking like that. But that crowding can become important when we look at big biological molecules later in the course. So remember how we're translating from this structural formula into the line structure: carbon, 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 carbon. 1, 2, 3, 4. So that's how we like to show the skeleton structure in the zigzag pattern. Good. All right, so let's keep going with our acyclic straight chain or non-ring type of alkanes. 4 is bute, so a butane is a 4-carbon alkane. 4 carbons in a row. 1, 2, 3, 4, or 1, 2, 3, 4. 1, 2, 3, 4. Okay, so now how do we want to think about this? Well, there are different kinds of structures that can be drawn depending on whether you have the carbons attached to each other in a straight chain or in a branched chain. And that's what I showed you before with the rings of the chain. And these are different compounds. They're called isomers. 2 different compounds with the same molecular formula. Notice that we've got butane here, which has carbon, 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 carbon. And how many hydrogens would you have to supply? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's why that's C4H10. Does that work for isobutane? Carbon, 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 and carbon. Let's supply those hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9. And that carbon has 1 bond, 2 bonds, 3 bonds, so it needs a hydrogen as well. That makes 10. You can count them all. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are all butanes, but straight chain 1, 2, 3, 4 is definitely different than this branched version. That's why this is called something different than straight butane. It's called isobutane. And we'll talk about that in a bit. That's a linear chain compared to a branched chain. Obviously, linear chain is all in the same line, and a branched chain obviously has a branch off of a linear portion of a chain. Okay. So let's talk about these 2 isomers. Butane and isobutane are called isomers of each other. Isomers, once again, this is going to be very important. 2 different compounds, okay, so they are definitely different, but they have the same molecular formula. They use the same number of atoms. We have this particular kind of isomer is called a constitutional isomer. Constitutional isomer. Constitution is one of the first things that defined and made what the United States became when it became a country. And so the Constitution is how the things are put together, are connected. It's another good example of constitutional isomers. C3H, 2 carbons, 3, 4, 5, 6 hydrogens, and 1 oxygen. 2 carbons, 1, 2, 3, 4, 5, 6 hydrogens, and 1 oxygen. Okay, so these are isomers because they have the same overall formula of C2H6O. But dimethyl ether is very different than ethanol because how things are connected. So these are the best lists for IUPAC, International Union of Pure and Applied Chemistry, the names for all the different alkanes. And it's really important that you remember I hope I got them all. The different prefixes. Meth for 1 carbon, eth for 2, prop for 3, bute for 4, pent for 5. Hey, the pentagon. Hexane 6, heptane 7, octane 8, nonane 9, and decane, like a decade, for 10 carbon compounds. And all of these are 2N plus 2. That's the general formula. Okay. We didn't write them. Okay. 2 different isomers for pentane. 1, 2, 3, 4, 5. 3, 4, 5. Okay, so that's pentane. We can also go 1, 2, 3, 4 with a methane, or not a methane, but a carbon off of one of the 4 carbon chain. 1, 2, 3, 4 with 1 carbon off of that. Or we can also go 1, 2, 3, 4, 5. So carbon, 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 and I'll let you add them up. I guarantee you that all of these have 5 carbons and 12 hydrogens. This is called isopentane, and this is called neopentane. And the straight chain is just called regular pentane. Okay. All right, so let's look at these. C, we already did A and B. 1, 2, 3, 4, 5 carbons in a row. 1, 2, 3, 4, 5 carbons in a row. This is the same molecule. It's not an isomer. However, for D, these are not isomers. This has 1, 2, 3, 4 carbons, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 hydrogens. This has 1, 2, 3, 4 carbons, but how many hydrogens? 1, 2, 3, 4, 5, 6, 7, 1 bond, 2 bond, 3 bond, 8. So this is C4H8, not the same molecule. And if it's not the same molecule, it's not an isomer. Okay, good. simple alkanes need to be classified. And they're classified as primary, secondary, tertiary, or quaternary. A primary carbon is bonded to only one other carbon. So for every alkane that's simple, we can look at every carbon and judge it as a primary, sorry about that, secondary, tertiary, quaternary. And I think it's pretty easy to figure out here. A secondary carbon is bonded to two other carbons. Tertiary is bonded to three. And a quaternary carbon is bonded to four other carbons. So you're looking at each carbon and you're deciding how many carbons are attached. And then count them up. Not hard, but important whenever we look at bonding down the road. So an example here, what kind of a carbon is this? Well, it only has one carbon attached, so it's a primary carbon. What about this one? How many carbons are attached? 1, 2. 2 hydrogens, so that's going to be a secondary. What about this guy? 1 carbon, 2 carbons, 3 carbons, so that should be a tertiary. And what about this carbon? Carbon, 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 carbon directly attached. 4 carbons attached. That's a quaternary carbon. These are all things that we're going to be asking you to be able to do by just looking at any molecule on a test or on a quiz. Okay, so this is one of those reasons why we had you looking at bonds and hydrogens attached so that you can make a decision. Let's add the atoms in that you know are carbons. Remember, at the end of any of these lines, we know that there are carbons. Good, so there are 3 carbons that are attached to this carbon, right? So that's got to be a tertiary carbon. Hey, how many hydrogens are attached to that? Well, if we have 3 carbons attached, we need 1 hydrogen attached. So those two things are certainly related, trying to decide how many hydrogens are attached and also how many carbons are attached to decide the classification of that particular carbon. Good. Should be able to do the same sort of thing here and do it relatively quickly. Right? The ends are always primaries, aren't they? Because they only have 1 carbon attached. Since this carbon has 1, 2 that are attached, that's secondary. This carbon has 1, 2 attached, so that's secondary. And this carbon has 1, 2 attached. So in straight chains, with nothing else special, everything on the inside of the chain is secondary, and the end caps are always primaries. What about this guy? Only 1 carbon attached, so that's a primary. That's a primary, that's a primary, and that's primary. The outer ones, right? That carbon has 1, 2 attached, so that should be a secondary. That should be a secondary. And then this guy in the middle has 1, 2, 3, 4, so that's going to be a quaternary carbon. Nice. Okay, next slide. So now let's start talking about naming. We always want to be able to name our molecule, because if we can name it, then we can know and categorize it and then know what it's going to do, both from a physical point of view and also from a chemical, a reaction point of view. Okay, so we're going to use the IUPAC naming. Nomenclature is just a German word for naming. And it's unique and unambiguous because we don't want pentamonium to mean 3 different possible compounds. We want it to be just the one. Now, when we talk about drugs, and we've been talking about a lot of different potential drugs that go into a potential COVID-19 treatment, we can talk about systematic names, which is what you're going to learn. The IUPAC name. Then we can learn the generic name, ibuprofen. Or then we can look at the trade name, which is what, you'll buy it, Motrin or Advil. So those are for drugs. These are specific compounds, and we're going to try to take care of these with their IUPAC names. All right, so let's talk about branch chain, because the linear chain are obvious. You just count the number of atoms in the chain, and you use the prefix and end with "ane." Now, the nomenclature of branch chains have 3 different parts. The parent name has you identifying the longest continuous carbon chain in the molecule, and it isn't always from straight across from left to right, as we'll see. Then we deal with the suffix. Remember, the suffix is at the end, unless there's something else like a functional group that's attached. And then the prefix is going to tell us all about the things that are attached to the carbon chain. Remember, this is for the ones that are branched. So the prefix, what are and where are the things that are hanging off the chain? The parent is, what's the longest chain? And the suffix is, what is the special functional group for the particular molecule we're looking at? Cool. So, acyclic alkanes. I warned you that the longest chain may not be all in the same horizon or horizontal line. You just have to look at it and count for sure. And it doesn't matter if it's straight or if it has bends, because we already decided that that was the same molecule. So it's all about looking and counting. And sometimes you have to count more than once. Like, for instance, 1, 2, 3, 4, 5, 6. Yeah, you could have done it that way, but isn't that the same? Isn't that the same where you have 1, 2, 3, 4, 5, 6 with one thing hanging off the second carbon in the chain? Or 1, 2, 3, 4, 5, 6 with something hanging off the second carbon in the chain. It's the exact same thing. You see what we're getting at? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Something hanging off the second carbon in the chain. These are the exact same compounds. Okay. So that's going to be one of the tricks or the important things to be able to do. Now remember, you know all the parent names for 1 through 10. So now it's all about doing the lines and deciding what the longest continuous chain is. You can't look at this and say 1, 2, 3, 4, 5, 6 because there's more. We look here and we say 1, 2, 3, 4, 5, 6, 7. As opposed to, let's see if I can get a different color here. As opposed to 1, 2, 3, 4, 5, 6. So 7 beats 6. So this is why you're going to decide that that's the better line. That's the better way to count. Can't just go 1, 2, 3, 4, 5, 6 here. Or 1, 2, 3, 4, 5, 6, 7, 8. We're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9. There's nothing that's longer than 9 continuous chain carbons. And so this is a nonane because it's a 9 carbon chain. And then we would do the rest of the names for the constituents that are sticking off at various points along the chain. That can be a little tricky. You just have to practice. And remember, it's important that you check and make sure. Rule 1. If you have 2 possible 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. Okay, so there's a competition between 2 chains of equal length, 2 7-carbon parents. So which one do we use? The greater number of substituents, the greatest number of pieces that are hanging off the chain. If we did this chain, we would have 1 group, 2 groups hanging off the chain. If we do this chain, we've got 1, 2, 3 substituents, and that's better. That's a simpler way to name it. Or it's more easily able to observe the molecule and write it based on the name. So, because of that, we go with 3 substituents versus 2. Okay, so a tiny little bit of practice for parent alkane here. How do we count the longest number? Well, sometimes you just start and try. 1, 2, 3, 4, 5, 6, 7, 8, 9. So going here to here, that's 9. 1, 2, 3, 4, 5, 6. That won't work. 1, 2, 3, 4, 5, 6, 7, 8. So the 9 is still winning right now. What if we went 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Aha. Nothing's going to beat 10, which makes this a decane. Good. Okay, rule 2 for naming the substituents. You use the same terminology for the parents. And whenever there are substituents that are just carbons and hydrogens, they are called alkyl groups. So instead of it being a methane, we drop the ane and add YL, so it becomes methyl or propyl, that kind of thing. So for this compound, we've got 1, 2, 3, 4, 5, 6, 7. So this is a 7-carbon chain. So we would call this a heptane. Obviously, this is a 1, 2, 1, 2, 2-carbon chains. So these are ethyl groups. and there's a pair of them, and this is a 1 carbon substituent, and so 1 carbon is a methyl. So there's 2 ethyls and 1 methyl on this 7 carbon heptane chain. So methyl, ethyl, propyl, butyl, pentyl, and hexyl are whenever we have 1 carbon, 2, 3, 4, 5, and 6 carbon substituents hanging off a particular chain. Gracious, let's go with isobutyl one last time. So there's our chain. We've got a CH2, and then we have our sort of Y looking thing. 1, 2, 3, 4. So there's the 4 carbon, but it's in that particular connection to the base chain, and that's what the isobutyl group is. Okay, now let's move on. Halo substitution. Halo or alkyl halides has to do with fluoro, chloro, bromo, or iodos. And that's all it is. It's just a fluorine, a chlorine, a bromine, or an iodine that gets attached. Okay, so we're going through our process of alkane nomenclature. How do we name alkanes? Rule number 3 is that you number the carbons, and you have to number the carbons in the right way. Because if you have 7 carbons, you can number it 1 starting on the left, or you can have 1 starting on the right. So how do you decide? First off, 1 substituent should have the lowest possible number. You would never start here because that 1 substituent would be off the number 6 carbon, whereas if you started here, it would be off the number 2 carbon. Lowest number possible for substituent. If you have more than 1 substituent, assign the numbers so that the first substituent gets the lowest number, not the total number is smallest. We want our very first substituent to get the lowest number. Okay? Think of this. Whenever we're going to go from name to line structure, it'll become obvious that we would rather start from the left to the right and have the substituents listed in terms of their smallest numbers, so that we can just say, okay, it's a 7 carbon chain, 1, 2, 3, 4, 5, 6, 7, and we've got a substituent at carbon 2, and 2 of them hanging off number 5. That kind of thing. I think whenever we go from line structure to name, and then we go from name to line structure, you'll see what we mean, why all these naming rules work best. So, once again, if the first substituent gets the same number either way, then we'll go on to the second substituent gets the lowest number. So here, if we started the numbering from the left, the first substituent is on carbon number 2. If we start numbering from the left to the right, the first substituent is carbon number 2. But how do we do this? 2, then 3, then 6. If we number from the left, we go 2, then 5, then 6. And 2, 3, 6, because the second substituent is a smaller number, beats 2, 5, 6. So this is how we would name this guy. Cannot be good at this until you start to practice. And also, another way to do it, if you have 2 different compounds or 2 different possible ways, write them both down and then look at the numbers and the names that you write, and then it should be obvious which one should be right. So, which one of these would you consider to be numbered correctly? Well, how do you decide? Well, you would decide whether or not the longest chain is correct first. So you go by for the first rule. If you say this is 1, 2, 3, 4, 5, 6, 7, hey, what if we went 1, 2, 3, 4, 5, 6, 7, 8? So this is an octane, not a heptane. So already we know that A can't be right. What about B? 1, 2, 3, 4, 5, 6, 7, 8. I think we got that other issue again. 1, 2, 3, 4, 5, 6, 7, 8. Same deal. There we go. Well, that's possible, or that's possible. So we're able to eliminate A and B right away. So now let's decide between C and D. If we go with C, the first substituent that is attached is on carbon 3. If we look at D, the first substituent is on carbon 3. So that's a tie. So let's just do the numbers for the substituents. For C, it's 3, then 5, then 6. 3, then 5, then 6. What about D? D goes 3, then 4, then 6. Well, what's better? 3, 5, or 6? 3, 4, or 6? It's D. D is the correct number. Okay, good. Ignore prefixes. On the substituents. Okay, so the prefix contains the location and names of each substituent, and you do them in alphabetical order. You precede the name of the substituent by the number of where it attaches on the chain. Then you separate the numbers by commas, separate the numbers from the letters by dashes. And if you've got multiple of the same substituent, then you use di, tri, or tetra. And these prefixes don't count when alphabetizing. Makes a lot of, like every time we do rules, especially in chemistry, it takes much longer to talk about the rules than it does to apply them. And you can't get good at it unless you practice anyway. So that's the way to do this. Let's go through a couple of examples. Cool. So we've got this compound. Let's see what it looks like, see how we decide. We've already decided that it's a parent name of heptane because it's got 7 carbons in its chain. And we've decided to name starting here because of the first substituent being a smaller number. And what else do we have? We've got methyl on 2 and methyl on carbon 3. And then we've got an ethyl on carbon 4. So 2,3-dimethyl is how we work on letting everybody know that we've got a methyl on both carbon 2 and carbon 3 in the chain. So what's next? Well, we have to decide whether ethyl comes first or whether di comes before methyl. And the answer is E before M. The ethyl comes before the methyl because we don't pay attention to the prefixes. And there you go. So notice that the commas separate the numbers 2,3-dimethyl, and the dashes separate the numbers and the letters. So 4-ethyl 2,3-dimethyl heptane is the name. More practice, more practice. Let's try another one. Let's see if I can find it here. Alrighty, found them in my notes. Boy, they look scary, don't they? They look crazy scary. There's no way. Oh, yeah. It's not too bad. Let's start thinking about it in a systematic way. Can you look at this and sort of piece out that that's going to be the longest continuous chain? I hope you can see that. Nothing else is going to be as long as that. So can you also tell that counting from here, 1, 2, 3, 4, and counting from here, 1, 2, 3, means that we're going to start the counting from here. So 1, 2, 3, 4, 5, 6, 7, 8. So this is an octane, right? Okay. So if it's an octane, what's hanging off where? Well, those are methyl groups, and so is that. So we've got 3, 3, 4, tri-methyl. And what else do we have? 1, 2. So that's 5-ethyl. Okay, so how do we put that together? There's 2 methyls off of the 3rd carbon, a methyl off the 4th carbon, and an ethyl off the 5th carbon. So what comes first? Well, ethyl beats methyl, so this becomes 5-ethyl dash 3, 3, 4 dash trimethyl octane. Good. Okay, what about the next guy? Oh my goodness, it's impossible. So many. Nah, I hope you look at this and you can see this as the longest continuous chain by far. You could try some of the other ones, but that counts out to 10. And I think it's also obvious that the first constituent comes off of that one. The first constituent comes way later. So we're going to start counting from up here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is a decane. What kind of decane? Well, it's got some things hanging off it. This is a 1, 2, 3, 4. So this is a 6-butyl group. This is off of carbon 5, 2 carbons. So that's 5-ethyl. It's also a 4 and 5 diethyl. And then we've got 3-methyl. Okay, so what comes first? Between butyl, ethyl, and methyl, the butyl comes first. So we've got 6-butyl. Then comes ethyl, 4, 5, diethyl. It's real easy to forget to write diethyl instead of just saying 4,5-ethyl. Can't do that because the number of numbers tells you whether it's di or tri. And then we've got 3-methyl. It's not that bad. You just got to practice. You can do it. Practice up. Get good at it. Next, we go from the names to the line formulas. And if you ask me, I think it's a lot easier to go this direction than the other direction. And I think it should be pretty easy whenever we go about the business of doing it. And I think for me, the easiest way to do this is to do the parent chain first and then just hang the substituents off it. That always seems to be the way that it works nicely whenever I'm looking at these problems. So it's a hexane, right? So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. If we decide that that's 1, 2, 3 methyl. That is it, guys. See how fast that went? Let's go with B, octane. 1, 2, 3, 4, 5, 6, 7, 8. We've decided already that the 1 starts here, so 3 and 4 dimethyl. So if that's carbon 1, 2, there's 1 methyl, and there's the other methyl on carbon 3 and carbon 4. Done. See how fast that is? Boy, whenever we go from name to formula, it's so much easier than formula to name, but that's the point. It should be easy to go from the name and think about what the structure of the compound is. That's the whole point to nomenclature. Okay, pentane, 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5. We've decided that number 1 always starts on the left, so we've got 3 different methyls, 2 of them off carbon 2, and 1 of them off carbon 4. That's all it takes. Not too bad. Hexane, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I always count them out. Carbon 2, carbon 4. 2,4-dimethylhexane. Nice. Good job. Let's keep going. Shucks. Come back to it again. 1, 2, 3, 4, 5, 6. So it's a hexane. The fluoro is on group 2. The tert-butyl is on group 3. The butyl beats the fluoro. So 3 tert-butyl, 3 fluorohexane. Nice job. Moving on. All right, so 2,3-dimethyl, 2-ethylpentane. That was incorrectly named. So how do we go about dealing with this guy? How do we fix this? Well, there's lots of different ways to think about it. What do you think is a good way to think about how to fix one that's messed up, or to try to figure out which one is correct compared to the one that isn't? Are you thinking about it? Are you trying to decide? Or are you just waiting for me to tell you? Oh, I hope you're not just waiting. I hope you're using your brain to think about it, to try to decide the best way to work through this problem. To me, I say, let's draw out what they think they got. Okay, this 2,3-dimethyl 2-ethylpentane, based on what those words tell you. And then once we look at the line formula, then we can go backwards and figure out what was done wrong. So if it's a pentane, we would go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Good. And then we would say 2,3-dimethyl. So if that's 1, say 2,3-dimethyl. And then we'd say 2-ethyl. So that's 1, 2. So 2,3-dimethyl, 2-ethyl pentane is what he has. If we do the counting right here, 1, 2, 3, 4, 5. Well, what if we did the counting not there, but 1, 2, 3, 4, 5, 6. Well, there it is. It's not a pentane. It's not. It's a hexane. It's got to be a hexane, right? So that means B and E, and clearly the original one is wrong. So we now have to decide what kind of hexane this is. Where would we start the counting? Would we start the counting here? Let me go to a different color. Pointer options. Let's go back to red. Okay, so we could count 1, 2, 3, 4, 5, 6. At which point our first substituent would be 3. Or we could go in the opposite direction, purple. 1, 2, 3, 4, 5, 6. So they both have 3s on them. Okay. How many substituents would there be if we went with the 1 that's red? Well, we would then go 1, 2, 1, 2, 3. And what if we went purple? If we counted purple, we would have 1, 2, 3. Okay, so the number of substituents is the same. So if we counted from the red, it would be 3, 4, 4 trimethyl, right? 1, 2, 3, 4, 4 trimethyl. And if we went with the purple, 1, 2, 3, 3, 4 trimethyl. So what's better? 3, 4, 4 or 3, 3, 4? It's got to be 3, 3, 4. That's why it's D. You with me? So while it feels like you could name this compound Cycloalkanes, now we're going to go with any one of these names. There's only one correct and how to name those. Way to name it. And it's that one. Good. Cycloalkanes, let's move on, are the ones that contain carbon atoms arranged in a ring. 3 carbon rings is cyclopropane, 4 carbon rings are cyclobutane, 5 is cyclopentane, and 6 is cyclohexane. Okay. And cyclohexanes, remember how they're different. They have 2 less H atoms than the acyclic alkane with the same number of carbons. 2 less hydrogens. That's how you can tell based on the formula whether or not you have a cyclo or a straight chain alkane. Okay. So how do we name these guys? It's the same way every time. You determine the parent. So how do you determine the parent correctly with the cycloalkane? If the ring has only one group attached, then you must count the carbons of the ring and the chain. And the more carbons equals the parent. Basically, it's all about how many carbons in the chain that make the decision on who the boss is in a compound. This is a 3-carbon ring and a 1, 2, 3, 4 carbon chain. And because it's 4 beats 3, the parent is butane. But here we've got 2-carbon chain attached to a 5-carbon ring. Ring, and 5 is greater than 2. That's why the parent is the cyclopentane ring. That's simple. What's the next? Or maybe we'll play around with further indications. If the ring has 2 or more groups attached, then we consider the ring to be the beast. It certainly works the best for us if we do it this way. And it's simple. And so I like simple. Let's go with cyclohexane, therefore, as the parent, and then you look at the substituents off the ring. Rule 2. We've decided that it is a cyclic compound, and it only has one substituent, whatever that cyclic compound is, with one substituent. You name the substituent followed by the parent. Simple enough. Substituent is ethyl here. The parent is the 5-carbon ring. So ethyl cyclopentane, done. No number because it's only a single substituent. Because if you decided, where would you decide to start the counting? And I could just rotate it by 1 to make the 1 different. So if there's only one substituent, it's obvious it has to be just simply ethyl cyclopentane, which says an ethyl group off a cyclopentane. Good. What are we going to name this thing? Since 113 is better, they're all methyl groups. So 1, 1, 3, try methyl, because they're all methyl groups. Cyclohexane. There you go. Excellent. Next, if we have 2 or more substituents are present and there's a tie, how will we go about thinking about that? If there's a tie, you number by alphabetical priority. So if it's 1, 2, 3, 4 or 1, 2, 3, 4, and you could do it either way. This is M for methyl. This is 1, 2, 3. So P for propyl. And sometimes I have to go through A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. So methyl beats the propyl. I have to sing. Sometimes I even sing in the middle of the tests, and you're allowed to sing if you wish. That's why we would make the numbering priority for the methyl to be number 1. So we're talking 1 methyl, 4 propyl. That tells us that there's a methyl group hanging off the first carbon, and then 2, 3, 4 right across from it. You have a propyl group hanging off the cyclohexane. Very nice, very nice. What's next? Well, it's about name generation. Prefix followed by the parent. Prefix followed by the parent. Always, always, always. So how would we go about looking at this guy? Prefix followed by the parent. Well, let's see. This is a methyl. This is two methyls. This is a ethyl, right? So we wouldn't start here because 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. So the smallest numbering, and we wouldn't start with 1 here because then there would be 1, 3, 3 trimethyl as opposed to 1, 1, 3 trimethyl. So you can see how you make the priority in 2-ethyl. So you're going to go through. What do we got? We got the parent as a cyclohexane because 6 carbons. So 2-ethyl because the ethyl wins because E is before M, followed by 2 1s and a 3 trimethyl. And you can't just call it hexane because it's cyclohexane. Good. Practice. The only way you get good at this is practice. And you'll make mistakes at the beginning because you'll forget commas, or you'll forget how to do the numbering properly, or you'll forget to say tri, or you'll forget to say cyclo, or you'll put the say it was dimethyl, you'd put the D in front of the E because it's got the prefix. There's lots of different ways to mess it up. You just got to practice, make your mistakes in practice so that you don't make them on the tests. IUPAC names for the following. Well, how would you go about doing that? You have to decide who's the boss, who's running the show here. Well, I think it's pretty clear who's running the show in that first one, right? Because you only have a 1 carbon hanging off a 3 carbon ring. So, who's the boss? Well, the boss is the cyclopropane, right? And if that's the cyclopropane is the boss, and it's got one thing attached, and that's a methyl group, then it's just simply methyl cyclopropane. Now, who's the boss here? Well, it's the ring, because it's got more than one substituent. That is a cyclohexane ring because it's 6-member, and it's a ring, so it's got the cyclo. We've got an ethyl group, and we've got a chloro group. So how do you do your counting? Well, you want to have that smaller number over here with the letter. So 1, 2, 3. So that's 1 chloro, 3 ethyl, cyclohexane. Nice. Okay, so who's running the show here? Who's the big boss? Well, we've got 3 different groups, right? Off 1 ring. So I'm pretty sure that the ring is going to be the boss. So it's 4 carbon ring, so it better be a cyclobutane, because this is a 1, 2, 3 carbon, and 4 beats 3. So it's cyclobutane. Do we have anything that's a cyclobutane? Cyclobutane. It's not one of those. That doesn't say cyclo at all. So it's either A or D. So now let's do our counting. it's either going to be, well, it's going to be 1, 2, 3, right? You wouldn't go 1, 2, 3, 4. So it's 1, 2, 3 for sure. So now we have to decide where we start our counting. One, 2, 3 is a possibility, right? Are there any other possibilities here? And you could count the other way. You could go pointer options, ink color. One, 2, 3. So we've got a methyl, an ethyl, and a propyl. And since the ethyl can't be number 1, ethyl is definitely going to be 2. What we want is the numbering between the start. M is greater than P, right? So we want M to be the 1. Okay, so if M is going to be the 1, then do we write it methyl first? Then ethyl, so it's 1, 2, 3? Absolutely not. It's not the numbering priority. It's the letter priority. And so that's why we've got 2 ethyl, 1 methyl, 3 propyl cyclobutane. That's it. That's how we work this one. Practice, 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 practice. There's no substitute for practice on naming. So you got to battle through. And don't kid yourself to think you know it unless you start to actually do it. And here's one more big hint. The naming, because it's IUPAC and they want it to be as systematic as possible, if you really work hard and know the alkane steps for naming, the steps for naming for all the other kinds of compounds are very similar. So if you study real hard and know the naming steps now, naming is easy the rest of the way. So there's no substitute for battle. So now we're going to go the opposite direction. We're going to go from the names and then draw the line formulas. These are quick. Cyclohexane, 1, 2, 3, 4, 5, 6. Now that's terrible. That is truly awful. So instead of being quite so messy, how about 1, 2, 3, 4, 5, 6. That's it. That's cyclohexane. That is just, that's ugliness. I'm not an art major. That's all I can tell you. Okay. Cyclopentane is the boss. So 1, 2, 3, 4, 5. There's 5. That's terrible, but it works. And then we've got 1, 2, 3, and 4 tetramethyl. So 1, 2, 3, 4. Doesn't matter. There you go. That's all there is to that guy. Cyclohexane. You can see where going from name to line structure is super fast. It doesn't matter where you decide 1 is. We're going to stick 2 methyls on the 1. 1, 2. And then you just count 3 more. 2, 3, 4. And there's your 1, 2 for the ethyl. That's it. There's lots of different ways to make that look, but that has to be that particular compound. Cyclohexane. 1, 2, 3, 4, 5, 6. Good. 1, 3, 5 trimethyl. So 1, 2, 3, 4, 5. That's it. See how fast that is? Man, I love going from names to line formulas. Good. What's next? Now that we've named and identified, now let's talk about some of the physical properties that go along with these particular kinds of compounds. Alkanes, the small ones, with only 4 carbons, 3 carbons, 2 carbons, or 1. These are small. Methane, ethane, propane, and butane. Hey, you know about methane gas. You may not know much about ethane gas. Propane gas? Oh yeah, you know what that's grills. Butane gas, you know what that is. That's a lighter. So what's the story on these? These guys are gases at room temperature. Now I know what you're thinking. Maybe you're thinking, oh, butane. Look, if I have one of those plastic lighters, you've seen them, and you can see the liquid inside. But if you press down on the little trigger to let the gas come out before you light it, it comes out as a gas. It's under a little bit of pressure inside the plastic container, and that leaves it in the liquid phase until it comes out. Same thing with a propane tank. There's liquid in there until it gets released from its pressure, and then it turns into a gas at room temperature. And these obviously are used as heating fuels quite extensively. Now, when we get slightly bigger alkanes with 5 through 8 carbons, pentane, hexane, 5, 6, 7, and 8, these are liquids at room temperature. And they're very volatile, which means go into gas state easily. That's all that volatile means. It means it easily goes from liquid into the gas state. And these are all used to make gasoline for your car. They're all sort of put together. When we talk about the octane rating in a car, it's really a series of alkanes that have 5 through 8 carbons in the chains. What else do we know? We know that when we get to even bigger ones, these guys are liquids at room temperature. And these are found in kerosenes, diesel fuel, or jet fuels. You pump gasoline at the tank on a hot day, and you can see the fumes coming off, that sort of waviness. You do that with a diesel fuel pump, and you can't see those fumes. That's because they're liquids at room temperature, and they stay liquids. So that's another reason why if you spill gas at the tank a little bit, it evaporates quickly. But if you spill diesel fuel, man, it sits there all day. That's why they have to put that stuff out there, the sand, and try to scoop it up, because it stays as a liquid at room temperature because they're bigger. Alkanes with 18 or more carbon atoms, these are really bigger, are waxy solids at room temperature, and are used in the waxy coatings that go on fruits and vegetables. They spray them on. I at one time worked at a oil refinery, not like taking it out of the ground, but what we did was we took the oil that's already out of the ground and we turned it into mineral oil and other things. Activated charcoal came out of it, activated carbon. They also found this stuff, or separated it out, in something that was called microcrystalline wax. And if you want to think about what microcrystalline wax is, buy juicy fruit gum at the grocery store. You know how the pack has that shininess to it? It's covered in microcrystalline wax. It's the same sort of stuff that's on your fruits and vegetables to make them shiny and retain their moisture. Alkanes, all of them, contain only non-polar carbon-carbon-carbon-hydrogen bonds because the electronegativities are very close. As a result, they are non-polar molecules that are alkanes, and they have only weak intermolecular forces. And that's why weak intermolecular forces means low melting points and low boiling points, and they easily go into the gas state or the liquid state. I think this is just stuff that you remember from 111. As the number of carbons in an alkane goes up, increases, the boiling point goes up. 4-carbon butane, the boiling point is on a really cold day, just below freezing. 1, 2, 3, 4, just one more carbon. 36, that's like a hot day. It doesn't boil until it gets into the 70s for us Fahrenheit people. In hexane, that's a very, 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 very hot day. That's in the 120, 130 Fahrenheit range. So just adding an extra carbon increases the boiling point because it's just a bigger molecule, which means bigger dispersion forces. What other physical properties do we have to think about? Boiling points of alkanes versus linear chains. The boiling point decreases for branched, whereas it increases for cycloalkanes. So why? Branched alkanes means they're more compact. So there's less surface area for the molecules to bump into other molecules, and it's those bump into other molecules that makes the dispersion forces greater. Think about it. If you had to run through a tight crowd and get through everybody, that's sort of going from the liquid to the gas phase. Would you be able to get through people if you were smaller or bigger? Oh, much smaller, right? So if you're smaller or you scrunch up, you can slip around through people much easier. And because of that, you don't bump into other people as much. And because you don't bump into, that means it's easier for you to boil off. And you can see, if you ran around with your hands out, you'd smack into everybody, you'd bump into everybody, and they wouldn't let you run. They'd get mad at you. They'd hold you down. You wouldn't get through them as fast. So the boiling point, as you get more and more branched, goes farther and farther down. Now, as for cycloalkanes, it increases because it's a more rigid structure, which means it's going to not be able to scrunch up, and that means it's going to bump into other stuff more. There's extra stability there. Okay. Combustion, that is the big time reaction that happens with alkanes. They do not react very much, but when they do react, it's through combustion. And that's because they have no functional group. No place where it's easy to react with an alkane. So they undergo few reactions, and we'll learn that as we go. That'll become really important. But combustion is one of the few reactions that will happen. And I know it feels like alkanes are very reactive because we burn gasoline and butane lighters and methane gas and propane tanks. But in fact, it's pretty hard to get those reactions to start. We will find lots and lots of other organic molecules that react super fast, super easy. And you know about combustion, right? They burn in the presence of oxygen gas to form carbon dioxide gas and water vapor, either gas or perhaps in the liquid state. Now, those products are always the same regardless of what alkane reacts. Methane reacts with oxygen gas to make carbon dioxide and water. And isooctane, a huge, lots and lots of carbons, reacts with lots more oxygens, but you're still only making carbon dioxide and water. You're just making more energy. Okay. Hey, just for fun, let's do C7H. Let's do C8H18 plus O2. That's octane plus CO2 plus H2O. So if we decide that's a 1, that has to be an 8. That has to be a 9 to make 18 hydrogens. So 9 oxygens plus 16 oxygens makes 25 oxygens on the right. To get 25 oxygens on the left, well, you have to have 12.5, and we don't do fractionals. So we start over, or we multiply all of these by 2. And if you multiply all by 2, it's 2 octanes plus 25 O2s goes to 16 CO2s plus 2 times 9 is 18 H2Os. Always check to make sure all your atoms balance out. But that's about as tough as the balancing is going to be in this class. Okay. So, if you've ever go into somebody's house where they were having some furnace work done and somebody's laying on the ground and they look like they had a real bad, too long of a session in the tanning booth, there's a problem. And the problem is incomplete combustion of the methane from the natural gas has occurred because you have a limited amount of oxygen down in the basement in a closed off room or something. And instead of making carbon dioxide, you're making carbon monoxide. And that's really dangerous because it binds to the hemoglobin in blood, and it binds tightly, more tightly than the oxygen whenever it binds to the hemoglobin in your blood. And as a result, whenever anything binds to the hemoglobin in the blood, it looks bright red. Whenever it's something that isn't bound, that's why your blood looks blue. It's only whenever something binds. But whenever you breathe in too much carbon monoxide, what you end up doing is binding much more of the carbon monoxide than the oxygen, and you slowly suffocate. So if you ever see that, you're in danger and that other person is in danger. Get out of there as fast as you can. Okay, solubility and density. Solubility is how it dissolves. Density means how heavy it is. Compared to the solvent that it's mixed in with. To solve it. Okay, so alkanes are insoluble. That's because they're mostly non-polar. And remember, like dissolves like. So water is definitely very polar. So because they're non-polar, they're insoluble. However, they are soluble because they're an organic compound in non-polar solvents, such as other alkanes, like dissolves like. And alkanes are also less dense. than water means they will float, right? The oil forms a thin layer on the surface. That's why it's so hard to go and get oil once there's a spill, because it spreads out so fast, so quickly. All right, good job. I think we're done. Let's get ready for set 3.